Hello everyone, welcome back to StudyMation's Computer Science series. Today we're going to talk about addition of binary numbers and the overflow error, subtraction of binary numbers, multiplication of binary numbers, logical binary shifts, and the two's complement. Before we start with the addition of binary numbers, there are some key facts to note. Note the following key facts when carrying out addition of two binary digits. This can then be extended to consider the addition of three binary digits. Here's a quick recap on the role of carry and sum. If we want to add the numbers 97 and 64 in decimal, we add the numbers in the right-hand column first, which is 7 and 4. If the sum is greater than 9, then we carry a value to the next column. Since 7 plus 4 is 11, we carry the next one to the next column. We continue moving left, adding any carry values to each column until we are finished. 9 plus 6 plus 1 is 16, and therefore our answer for 97 plus 64 is 161. Adding in binary follows the same rules, except that we carry whenever the sum is greater than 1. Now let's add two binary numbers. Over here we have two 8-bit binary numbers to be added. We're going to start off by adding the numbers in the right-hand column first. By the binary addition rules, we know that 1 plus 0 is 1. 1 plus 1 is 10, which has a sum 0 and carry 1. 1 plus 0 plus 1 has a carry 1 and a sum 0. 1 plus 0 plus 1 again has a carry 1 and a sum 0. 1 plus 0 plus 0 has a carry 0 and a sum 1. 1 plus 0 has a carry 0 and a sum 1. 0 plus 1 has a carry 0 and a sum 1. And 0 plus 0 has a carry 0 and a sum 0. Therefore, adding 0, 0, 1, 0, 0, 1, 1, 1 and 0, 1, 0, 0, 1, 0, 1, 0 give us the answer 0, 1, 1, 1, 0, 0, 0, 1. Now let's talk about the overflow error. Now let's consider this example. We are going to add 0, 1, 1, 0, 1, 1, 1, 0 and 1, 1, 0, 1, 1, 1, 1, 0. Both of these binary numbers are 8 bits. 0 plus 0 has a carry 0 and a sum 0. 1 plus 1 has a carry 1 and a sum 0. 1 plus 1 plus 1 has a carry 1 and a sum 1. Again, 1 plus 1 plus 1 has a carry 1 and a sum 1. 1 plus 0 plus 1 has a carry 1 and a sum 0. 1 plus 1 plus 0 has a carry 1 and a sum 0. 1 plus 1 plus 1 again has a carry 1 and a sum 1. 1 plus 0 plus 1 has a carry 1 and a sum 0. Now there are no longer any numbers to be added, but we have an extra bit of 1 left. This addition has generated a 9th bit. The 8 bits of the answer are 0, 1, 0, 0, 1, 1, 0, 0. This gives the denary value of 76, which is incorrect because the denary value of the addition is 110 plus 222, which gives us 332. The maximum denary value of an 8-bit binary number is 255. The generation of a ninth bit is a clear indication that the sum has exceeded this value. This is known as an overflow error, and in this case is an indication that a number is too big to be stored in the computer using 8 bits. The greater the number of bits which can be used to represent a number, then the larger the number that can be stored. For example, a 16-bit register would allow a maximum denary value of 65535 to be stored. A 32-bit register would allow a maximum denary value of 4294967,295 and so on. Now let's talk about the binary subtraction. The rules are as follows. 0 minus 0 gives us 0. 1 minus 0 gives us 1. 1 minus 1 gives us 0. And 0 minus 1 is a carry. Considering the rules of binary subtraction, now let's do an example. Now let's consider these numbers for the binary subtraction. We have 10101101, 11001111. Minus 1 is a 0. We know that from the binary subtraction rules, and that is also true for the denary system. Now 0 minus 1 is not possible, so we borrow 1 from the next column. So we make that 1 0, and we carry the 1 to the right side. Now we don't consider this 1 0 as 1. Instead, we consider this 1 0 as 2, because the binary number 1 0 is equivalent to the denary number 2. Now 2 minus 1 is 1. Again, we have 0 minus 1, which is not possible, so we take the number from the next column and make that 1. Now 1 0 is equals to 2, so 2 minus 1 is 1. Now 0 minus 0 is 0, and 0 minus 0 is 0. 1 minus 1 is 0. 0 minus 1 is not possible, so we take the number from the next column. And 1 0 is equivalent to 2, so 2 minus 1 is 1. And then the 0 comes down. So the answer of this subtraction is 0 1 0 0 0 1 1 0. So that's how you subtract any binary numbers together. Now let's talk about the binary multiplication. Binary multiplication is just the same as denary multiplication. Now, for example, we have these binary numbers to be multiplied together. We have 101, 101, and 101. So we're going to multiply each digit from 101 with the digits above. So 1 into 1 is 1. 1 into 0 is 0. 1 into 1 is 1. 1 into 1 is 1. 1 into 0 is 0. 1 into 1 is 1. Now we leave a gap and go to the next number. So 0 into 1 is 0. 0 into 0 is 0. 0 into 1 is 0. 0 into 1 is 0. 0 into 0 is 0. 0 into 1 is 0. Now we leave 2 digits and multiply the next number. So 1 into 1 is 1. 1 into 0 is 0. 1 into 1 is 1. 1 into 1 is 1. 1 into 0 is 0. And 1 into 1 is 1. Now we're going to add these numbers together. So we have 1, 0. 1 plus 1 is 1 plus 1 is 0 and 1. 1 plus 1 is 0 and 1. 1 plus 1 is 0 and 1. 1 plus 1 and plus 1. 1 plus 1 plus 1 is 1 and 1. 1 plus 0 is 1. And 1 plus nothing will come. So our answer for 101101 multiplied by 101 is 111000001. And that's how you multiply any binary numbers together. Now let's talk about the logical binary shifts. Computers can carry out a logical shift on a sequence of binary numbers. The logical shift means moving the binary number to the left or to the right. Each shift left is equivalent to multiplying the binary number by 2, and each shift right is equivalent to dividing the binary number by 2. As bits are shifted, any empty positions are replaced with a 0. There is clearly a limit to the number of shifts which can be carried out if the binary number is stored in an 8-bit register. Eventually, after a number of shifts, the register would only contain zeros. For example, if we shift 0, 1, 1, 1, 0, 0, 0, 0, 5 places to the left, in an 8-bit register would end up with 000000000. This makes it seem as though 112 multiplied by 32 is equals to 0. This would result in the generation of an error message. Now let's do some examples. Now for example, we have the binary value 00010101, and we're told to shift the bits in this register one place to the left. This means each digit will be shift one place to the left. And this would give us 0, 1, 0, 1, 0, 1, 0, 0. We can see that one value from the original number from the left is deducted and one value to the right is added. Now we have another example, but this time we're told to shift the bits in this register one place to the right. This means we're told to shift each value one place to the right. This would give us the value 0, 0, 1, 0, 0, 1, 1, 0. This is the same as removing one number from the right and adding 1 0 to the left. Now what if we're told to shift the original number 2 places to the right? In this case, we would get the value 0, 1, 0, 0, 1, 1, 0, 0. This is the same as deducting 2 values from the right and adding 2 zeros to the left. Now let's talk about 2's complement. Up until now, we have assumed all binary numbers are positive integers. To allow the possibility of representing negative integers, we make use of 2's complement. In this section, we will again assume 8-bit registers are being used. Only one minor change to the binary headings needs to be introduced here. In 2's complement, the leftmost bit is changed to a negative value. For instance, for an 8-bit number, the value 128 is now changed to negative 128. But all the other headings remain the same. This means the new range of possible numbers is negative 128 to positive 127. It is important to realize when applying 2's complement to a binary number that the leftmost bit always determines the sign of the binary number. A 1 value in the leftmost bit indicates a negative number, and a 0 value in the leftmost bit indicates a positive number. For example, 0, 0, 1, 1, 0, 0, 1, 1 represents 51. But 1, 1, 0, 0, 1, 1, 1, 1 represents negative 49. The positive binary number 19 can be written in the 2's complement format as shown: 0, 0, 0, 1, 0, 0, 1, 1. We can see here that 16 plus 2 plus 1 is equals to 19. The positive binary number 4 can be written in 2's complement format as shown: 0, 0, 0, 0, 0, 1, 0, 0. Now let's write negative binary numbers in 2's complement format. So negative 109 can be written in 2's complement format as shown: 1, 0, 0, 1, 0, 0, 1, 1. The 1 on the leftmost side indicates that it is a negative number. And this is also true for the denary value. We can see that negative 128 plus 16 plus 2 plus 1 is equals to negative 109. Now let's write negative 11 into 2's complement format. And that would be 1, 1, 1, 1, 0, 1, 0, 1. Negative 128 plus 64 plus 32 plus 16 plus 4 plus 1 is equals to negative 11. Consider the number positive 67 in 8-bit 2's complement binary format. It will be 0, 1, 0, 0, 0, 0, 1, 1. Now let's consider the number negative 67. One method of finding the binary equivalent to negative 67 is to simply put ones in their correct places. 1, 0, 1, 1, 1, 1, 0, 1 is equivalent to negative 67. However, looking at the two binary numbers, there is another possible way to find the binary representation of a negative denary number. First, write the number as a positive binary value, in this case 67, is equivalent to 0, 1, 0, 0, 0, 0, 1, 1. We then invert each binary value, which means swap the ones and zeros around. This would give us 1, 0, 1, 1, 1, 1, 0, 0. Then add 1 to that number. 1, 0, 1, 1, 1, 1, 0, 1. This gives us the binary for negative 67, which is 1, 0, 1, 1, 1, 1, 0, 1. This is another method of finding the binary representation of a negative denary number. That's all for today. Thank you for watching Study Mation animated educational videos.